Okay, this is just going to be going through just a bunch of derivatives to practice practice computation. So this is just a list of formulas that we'll need to know when doing derivatives, and it's really good to have these memorized. For the trig functions, I think the most important ones to memorize are sine and cosine, because all the rest can be derived through the quotient rule if you forget or unsure or if you don't trust your memory. So we may just do some problems. Have like, say we had f of x is equal to 3x squared minus 2 cosine of x. So the rules that we would use here are first the constant rule. So we have these coefficients in front of these common functions that we know. So when we do derivatives, we can essentially ignore those constants and only look at the more interesting functions. We have the addition rule. So yes, it's subtraction, but subtraction is just the adding the additive inverse, so it's not a big deal. But the idea is that since we have a sum of two functions, what we can do is just take the derivative of each thing, each summand in the sum, and so kind of split it up even further. And we'll be using the power rule. So the power rule, that's when we have something like x to the integer power, or sorry, x to the number power. This is a 2. The power rule is used for these types of functions, like x squared. And then finally, we have just the trig derivative of cosine. All right, so just going through each of them. So let's first maybe use for the addition rule. When we find the derivative, we're finding the derivative of each part and then subtracting them. Okay, and then maybe we'd use the constant rule, saying that we can just take these.
We don't feel any sensitivity.
And then finally, we can just use the power rule and derivative of cosine. So derivative of cosine is negative sine. So this is power and trig, we can say. Okay, so then just making it nicer, it's 6 plus 2 sine x. Okay. Does that make sense? So just using all those rules. All right, could do another one. Let's do f of x is equal to sine plus 1/2 cotangent. Okay, so maybe I won't list out all the rules, but we can go through it step by step. So first we would use the addition rule. So we can split up into, we can just take the derivative of each. And then so here we could use the fact that the derivative of sine is cosine. And then maybe we could use the constant rule here. You don't always have to do all these steps, but when you first start, it might be good to do these. And then finally, we can do the derivative of cotangent, which is negative cosecant squared of x. So maybe good to just kind of go over, let's say you forget what the derivative of cotangent is. So we can just practice doing that. So cotangent is just cosine over sine. So now we can use, so knowing that, we can use the quotient rule. So the quotient rule says that we have first the derivative of the numerator, negative sine, times the denominator, sine, minus the derivative of the denominator, cosine, times the numerator, cosine, and divided by the denominator squared. Okay, so the numerator is negative sine squared minus cosine squared. We have divided by sine squared. From here, notice the numerator, if you factor out -1, we have sine squared plus cosine squared. Now this is a Pythagorean identity. Sine squared plus cosine squared is equal to 1. So this becomes -1 over sine squared, and which is the same thing as negative cosecant squared. Okay, so that's how we can justify this step. And you don't have to do that every time, but it's good practice. Okay, let's do another one. And please stop me if you have questions. Let's do x cubed cosine of x. Okay, so for this one, we notice that this is actually a product of two things, right? It's a product of x cubed and of cosine. So using the product rule, or derivative, would be take, and it doesn't matter which you do first, but you take the derivative of one of them and multiply it by the not derivative of the other, and then plus the derivative of the other times the first with no derivative. Okay, so now we can just use the power rule, and that we know what the derivative of cosine is. So it's 3x squared cosine, and then minus sine x cubed. And we usually like to put the x cubes in front, or the powers in front. So it makes it look nicer. That's a derivative. Okay, so that was the one with a product rule. Let's do another one. Let's do.
Yeah, perfect.
2 minus tangent of x. Okay, so this one is a quotient rule. So the derivative, we take the derivative of the numerator times the denominator and then minus the derivative of the denominator times the numerator, and all divided by 2 minus the denominator squared. Okay, let's just do it. The derivative of x is just 1, so we have 2 minus tangent minus. Now here, the derivative of 2 minus tangent, we can use the sum rule. So this is really the derivative of negative tangent and times 2 minus tangent squared. So a big thing to note is that you cannot cancel out the 2 minus tangents, right? There would need to be a common factor in the numerator in order to do that. Oh, and by the way, so for here, what I'm doing is the derivative of 2 minus the derivative of tangent. So the reason why I didn't put the derivative of 2 there is because that's 0. If this is 0. Okay, so let's just do this. So we have 2 minus tangent. The minus and the minus make a plus. Their tangent is secant squared. And might as well put the x out in front. And then divided by 2 minus tangent of x squared. Okay, it doesn't look like there's anything else you can do more from here, so maybe just leave it like that. All right, let's do another one. Say our function is secant divided by 1 plus secant. So again, I cannot cancel secants, right? Secant is not a common factor in the denominator, so that's not allowed. So let's use the quotient rule. So the derivative of secant times the denominator 1 plus secant minus the derivative of the denominator times the numerator, all divided by the denominator squared. Okay, so just do it. The derivative of secant is secant tangent. Then we have a 1 plus secant. And then minus, so the derivative of 1 plus secant is also secant tangent. And with the other secant makes secant squared. So maybe a couple of things we can do to kind of make this easier to calculate or just simplify is that notice there's a common factor of a secant tangent in numerator and denominator. So what we could do is let's just take that out. Usually I like to leave things factored. So we have a 1 plus secant and minus what's left over here when we factor out a secant tangent is a secant. Okay, so that's really nice. So now that cancels out. So the secant and secant go away, and we have secant tangent divided by 1 plus secant squared. That's it. Great. Here's another one. Let's say we have radical x times sine. So just introduce a radical. So we use the product rule, right? We have product of two things. We have product of radical x times sine. So our derivative is you take the derivative of the first then multiply that result by the second, and then add the derivative of the second times the first. Okay, so when doing derivatives of radicals, notice that square root is just x to the 1/2. So we can use the power rule on this. Okay. So using the power rule, we have 1/2 x to the 1/2 minus 1, and derivative sine is cosine. Okay, so 1/2 minus 1 is negative 1/2. So that's a 1/2 in the denominator. Okay, so you could just leave it like this, or if you want, you can combine the two fractions. So you could leave it like this, but you could just combine and have sine of x plus 2x cosine divided by 2 radical x. So I'm just multiplying by 2 radical x for the second term there. And if you really wanted to, you could rationalize the denominator as well. So either of these are fine. So I have 2x radical x. So one thing to note that x times radical x is x times x to the 1/2. So that's x to the 3/2. So this is x to the 3/2. You can also, if you like radical form better, this is also radical x cubed. Since I wrote a radical there, let's maybe write a radical here. All right, and that's what you'd have. But either way is fine. This is probably fine as well. Okay, let's keep going. Let's say you have f of x is equal to sine, or sorry, let's do 1 plus sine divided by x plus cosine. So just another quotient rule. Okay, so the derivative, again, it's very nice once you come up with these formulas, right? It's at this point, it's very easy. You just need to plug it into the formula. And I can't stress enough, it's good to kind of write every single step out first until you kind of get used to the formula. And it helps you memorize the formula if you write everything out. Okay, so let's just take each derivative. So derivative sine is cosine. Factored first, because maybe something can factor and cancel, but I'm not sure yet. Oh, this is not a plus. I'm sorry, this is a minus. It's one thing to be very careful about. That can really change your answer. Okay, so I have 1 minus sine and 1 plus sine. Okay, from here, we can actually, instead of having to worry about all this, notice that this is a difference of 2 squares, right? 1 squared, yeah, so Yeah, this is the factorization of difference of two squares. So this, if you were to expand this out, you get 1 minus sine squared, which we know what that is. It's cosine squared. So that could help. That this is cosine x plus cosine, and we have a minus cosine squared. And from here, we can factor to make simplifying a bit easier. In the numerator, we have a common factor of cosine. And when we factor that out, we're left with one of the cosines up here. And here we can simplify easily. So the numerator just becomes x cosine of x, and then same thing, x plus cosine of x squared. All right, and that's it. We'll do one with tangent lines. So let's say we want to, or we're tasked to find the equation of the tangent line. To secant, or I could just write out the function. Secant of x at the point pi over 3 comma 2. So we know that so the equation of any line, right, is y minus y1 is equal to mx minus x1 over 0, whatever you prefer. And we have a point. We have pi over 3 comma 2. So but what is m? Well, that's exactly what the derivative tells us. M is the derivative at pi over 3. So our goal is to find out what the derivative is of secant and what is it at pi over 3. So let's find that out. So first of all, let's just find out what the derivative of secant is, and then think about at pi over 3. So we know what that is. The derivative is secant tangent. And at pi over 3, we have secant of pi over 3, tangent of pi over 3. Okay, so let's calculate that. For me, honestly, I don't really remember all the secant, tangent, cosecant, cotangent. I don't necessarily remember those angles, what those functions are at those angles. So, I mean, if that ever happens and you forget, just write it out in terms of sine and cosine. So if you know the sine and cosines, it's easier to, it's less things to memorize. Oh, sorry, this is tangent, not cotangent. All right, so we know these things hopefully. Sine of pi over 3. So again, if you forget, let's draw the circle. Pi over 3 is the one up there. And this one is a 1/2 radical 3 over 2. So sine is radical 3 over 2. And cosine pi over 3 is 1/2. So you get radical 3 over 2 divided by 1/4. This is radical 3 over 2 times 4 is equal to 2 radical 3. Okay, so plugging that in now to our tangent line, we have y minus 2 radical 3 x minus pi over 3. And then we could just leave it like that. Okay. Let's do another one like that. So let's do the same question, equation of tangent line. Let's do x plus cosine. And let's say at the point.
They're allowed to play.
1.
It's really clean.
All right, so again, the line is y minus y1 is equal to m x minus x1. So we know what the point is. It's y minus 1 is equal to m x minus 0. And with our calculus, this is y minus 1 is equal to f prime of 0 and x minus 0. So maybe it looks nicer to write it like this. Okay, so the goal is to find f prime of 0 and plug it into our line equation. Okay, so f prime of x, we use the sum rule. So the derivative of x is 1, and the derivative of cosine is negative sign. So that's our derivative. And plugging in 0, 1 minus sine of 0, and sine of 0 is 0. Okay, so that means our tangent line is y is equal to x plus 1. That's it. All right. It's actually a fun one we could do. So we haven't really talked about this much in class yet, but it's not too hard to think about, but about higher derivatives. So conceptually, we don't really know what this means right now. However, it's not hard to kind of understand is that what we'll call the second derivative is just the derivative of the first derivative, right? The derivative is a function, right? And we can take derivatives of functions. So it's not hard to believe that we can just take the derivative of a derivative. It's just a function. So, for example, so sometimes we might say, to use this notation, we might say that instead of the double prime, we could use this notation and say like d squared and over dx squared instead of d dx. And again, I haven't yet kind of discussed the meaning of that symbol, but yeah, so that's just right now, that's just a symbol. So let's just do kind of an easy example. If I want to find the second derivative of x squared. So what I do is, well, I want to find the derivative of x squared and then take the derivative of that result. Okay, so the derivative of x squared is 2x. And then the derivative of 2x is 2. So that's the second derivative of x squared. So let's maybe do another one. We could do let's do the fifth derivative. So we're going to do it 5 times of, let's say, x cubed. So you should have an idea about what the power rule does. You should have an idea what this automatically should be. Let's kind of go step by step. So much like the second derivative, all we're doing is we're taking derivatives 5 times. So first we take the derivative of x cubed, get 3x squared, and then we take the derivative of 3x squared, and we get 6x, and then we take the derivative of 6x, we get 6, and then we take the derivative of 6 and we get 0, which is 0. So you can kind of think of a pattern, right? At least for polynomials. What do you think happens? So when did we hit 0? Right, we hit 0 after 4 derivatives, right? And let's see what happens at every time we took a derivative. So after the first derivative, we got to a quadratic. After a second derivative, we got to a linear. After a third derivative, we got to a constant. And then at our fourth derivative, we got 0, which is also constant, but the fact that it's 0 is important. So now what is the idea is that, well, notice that the power decreases by 1. After every derivative. So this should tell you that since that's true, right? If power decreases by 1 after every derivative, that like at 3 derivatives, this will be constant, right? At which the fourth one would be 0. So we can make a claim, which is not too hard to see, is that if a polynomial has degree n, so that means this is the highest power of x, that doing one more than the degree will always give you 0, right? In fact, and all powers higher, right, will always give you 0. So for m greater than or equal to n plus 1. So, and again, that's we haven't really talked about higher derivatives, but it's not really too different than derivatives. You're just taking the derivative a couple times. So polynomials have this nice property, and actually another function has this kind of interesting property when it comes to higher derivatives. So let's do it for sine. Higher derivatives of sine of x. So
Just relaxing. Yeah.
for sine of x, our first derivative we know is cosine. And then let's take the derivative of this.
Air everywhere.
It's negative sine. So so we take the third derivative. We take the derivative of negative sine, and we get negative cosine. And then something interesting happens at the fourth derivative. So sometimes when for some notation. When it gets higher than probably 3, you could do it for 4, but if you put a little, kind of looks like an exponent, but with a parentheses around it, this will
Good.
denote the
Everything looks fine. Okay. All right. Well, enjoy the rest of your weekend. If anything
All right,
pops up,
so-
now next time, let me know. But otherwise,
here we just take the
Okay.
derivative.
all right. Take care.
Derivative of negative cosine. Oh, here. Derivative of negative cosine. And that's negative sine is sine. So that's interesting. Our function goes back to sine after 4 derivatives.
Fluoride feels sticky. It helps protect you.
So taking 4 derivatives of sine brings us back to sine.
For 1 hour.
And notice that this will repeat, right? Right, the 5th derivative
Oh, yeah.
will surely be cosine.
I know it's cold.
I think someone's mic is on. I'll just. Okay. So the 5th derivative will obviously be cosine, right? The 6th derivative will be the derivative of that, negative sine. The 7th derivative will be negative cosine. And the 8th derivative will bring us back to sine. So there's a pattern here, right? When you take every 4 derivatives, you can get sine. And then, of course, maybe every time you do 4 derivatives and then do 1 more, you get cosine. Every 4 derivatives and then 2 more, you get sine, and every 4 derivatives and 3 more, you get cosine. So we can use this to we can find the derivative of really anything for sine. So we could even do let's do f of 73, the 73rd derivative of sine. So we know if 73 is a multiple of 4, it's not, but if 73 is a multiple of 4, then f 73 of sine is equal to sine. So if it's a multiple of 4 plus 1, we get cosine. If it's a multiple of 4 plus 2, we get negative sine. If it's a multiple of 4 plus 3, you get negative cosine. And that's all you can do, right? It can either be a multiple of 4, 4 plus 1, 4 plus 2, 4 plus 3. So what we can do is actually, we can just do long division. Well, long division will solve this for us, right? So let's take 73 and divide it by 4. The remainder, maybe I shouldn't write it there. The remainder will tell us which is correct. All right, so let's take 4 into 73. So we have 4. 4 minus 7 minus 4 is 3. 4 into 33 is 8. And we have remainder 1. Okay, so what does that mean? Is that, let's think of the number 73. At every time you're looping 4, you're getting back to sine. So you're taking 18 cycles of getting back to sine. So if you think about it, at f of 72, this tells us you should get cosine. Now, if you take one more, f of 73, that's just the derivative of cosine, which is negative sine. So it's a neat little trick, and it's higher derivatives that kind of look nicer for these periodic functions. Not as nice with like tangent and those other ones. We can even like do higher derivatives of tangent just to see what happens. But yeah, why don't we just do that? Let's think about higher derivatives of tangent, and something not as nice happens. Okay, so let's first just take the derivative of tangent. This is secant squared. And now let's take the derivative of secant squared. So there's one more rule that that we'll actually do Monday next class called the chain rule, which will kind of make this a little bit easier. Which I could maybe talk about that a little bit later. Maybe after this, I can just at least not prove it, but just give you the formula and do some practice with it. But there's a couple ways of approaching the square of a function. If we don't have chain rule, whatever that is, we can just treat this as a product, right? The square of something is just times itself, right? So for now, let's just treat this as a product. So where both functions are the same. So the derivative of secant times secant would be the derivative of secant times secant plus the derivative of secant times secant. Or we can even just say 2 times the derivative of secant times secant. Okay, so what is this? This is 2 secant tangent times secant, or 2 secant squared times tangent. So already you can see we're kind of getting kind of far away from where we started at tangent. Like it's still there, but I mean, a couple of things like this is the derivative, right? And this is the function itself. So you can think of tangent as a function. Second derivative is twice the first derivative times the function. But it's just an interesting note right now. But maybe let's even take like a third derivative and see what happens. So 2 secant squared times tangent. So we can take the 2 out by our constant rule, or no, sorry, not that. We can take our 2 out by the constant rule and only look at secant squared times tangent. So we actually, maybe even nicer. Why don't we write it in this notation? We know that secant squared is f prime. Might be even easier to work with, and we know that tangent is f. So what is this going to be? It's going to be 2 times, so the derivative of the first is f double prime times the second. Then we have f prime times f double prime. So we're getting pretty far away from when we started, right? So 2 f double prime f plus 2f prime f double prime. So actually maybe factoring maybe looks easier. So yeah, that's it. We can plug in for what we have, right? This would be, was it 4 secant squared tangent? And then what's f is tangent plus secant squared. So tangent is not as nice as sine and cosine, right? We don't really come back to our starting point. But I mean, there's still kind of a nice relationship, right? When you take the derivatives, they all kind of like relate to each other. But maybe kind of coming up with a formula for higher derivatives might be harder, at least for tangent. So that's kind of right now I won't talk about for higher derivatives, but again, it's not too different. But maybe for those of you here, did you have specific questions, or you want to see maybe certain types of problems? So
I had a question
yeah,
about so during class, the first problem that we did, which was the f of x is equal to cosine of x, and we were trying to find the derivative,
yeah,
and you were just proofing through it. Obviously, I think you said that it doesn't, like, the process doesn't matter as long as we know that like f prime of x is equal to negative sine of x.
mhm,
There was one instance that I kind of got confused on, and it was towards the end where you took out cosine of x, and then it was cosine of x limit h as h approaches 0, negative sine of h over cosine of h plus 1.
okay, yeah. We maybe
And you said that that one is equal to 0, and I don't quite understand why.
sure. It's good practice anyway to kind of go through it. So we can go through it again. So yeah, so this is proving what the derivative of cosine is. So like on a test, I would say explicitly, like, use the limit definition to say what the derivative of cosine is. So yeah, so we know that it's negative sine. So this is proving that. So we'll just go through it step by step and then come to where you had the issue. So first, what we did was we used the sum formula on cosine, right? That's cosine x cosine h minus sine of x sine of h. And then we have minus cosine of x all over h. So the idea and how you approach this, we see that we have a sine of h over h term, which that's a nice limit that we have, right? That the limit as h goes to 0 of sine of h over h is equal to 1. Right, that's using the limit that we proved. So the first step in here would be maybe to split up the fraction. And let's have cosine x cosine h minus cosine x over h. And then we have minus a limit as h goes to 0. So this is minus non-equal of sine of x sine of h over h. Is that okay?
Yeah, that makes sense.
So let's just maybe take this one first. Notice that sine of x, there's no h there, right? So do you agree that as h is changing, sine of x is not changing at all, right? So
Yes.
so kind of acts as like pretend like it's just you're just fixing it as sine of x. So as h is changing, like this term is not going to be changing at all. It's always going to be sine of x. So we can think of this just as, well, let's just take the limit, or maybe this would be a easier way to see it. So remember we had our product rule for limits, right? We could take the limit of each thing in the product. Is that, you remember that rule? Like if you have a product of two things, then you take
Yeah,
the
that
limit
makes
of
sense.
each thing. So this is just sine of x, right? As h goes to 0, well, there's no h in sine of x. So of course, that's just approaching sine of x, right?
Yeah, that makes sense.
And then this approach,
Down would just be 1, right?
yeah, by our form. So yeah, so that completely takes care of that term then. And then we have this limit over here. Now we can actually just focus on that. So now we can do the same thing like what we did with sine. We can do on this side of the limit, if we factor out this cosine, this common cosine here, if you factor that out, we get, cosine of h minus 1 over h. Is that okay? So I just factor out the cosine.
Yeah, that makes sense.
So now we can just do the same thing that we did for the sine thing, right? And just split up the product. And then, right, this one has there's no h there. So that one is sine. Or sorry, it's cosine. So is that where you're confused?
No, it happens a little bit after.
Okay.
So this one, I remember you just multiplied by the numerator conjugate.
Yeah, like quote conjugate, cosine of h plus 1, cosine of h plus 1. Right, so the numerator becomes, what is it? Cosine squared minus 1. And what does the numerator become?
I think I remember you talking about something of this circle, so it's like cosine squared of h minus 1 is the same thing as negative sine of h.
Yeah, exactly. Right, this comes from, right, cosine squared plus, or maybe we should use h. Cosine squared plus sine squared is equal to 1, right? So if you solve for cosine squared, or if you solve for sine squared, you get sine squared is equal to 1 minus cosine squared minus 1. Sorry, sine squared is 1 minus cosine squared. Right, so if you multiply by -1, you get negative sine squared. It's equal to cosine squared minus 1. Yeah, so right, so this is negative sine squared of h over h cosine of h plus 1. Okay. Yeah, so at this point, what can we do? We can use we can write out explicitly. There's two things going on here, right? We have, let's take out one of the signs and the H. And then let's put the leftovers over here. You see what I'm doing there? I'm just taking out the sign and the H in the product.
Yeah, I see that, but see, like when we're doing a problem, how, like, what would the thought process be behind like the decision, that decision that we make to basically take the factors of sine squared h?
Yeah, why do you choose this factor? It's because we know what this is, right? It's kind of, think of it as, this is our way of simplifying fractions with limits, right? Like when you do like with, with normal fractions, right? You would be looking for common factors and canceling, right? That would be your method of simplifying. So this is like a new method or an additional toolbox in our method of simplifying is kind of looking for sine of h over h factors, because it simplifies it, right? This sine of h over h factor, limits to 1. So it's kind of just like simplifying when you have limits to 0 with sine of h over h. Does that make sense? Like you're kind of keeping an eye out for this term, right?
Yeah,
this term,
okay, I see that now. Yeah,
like here, that should tell you, oh, I know what to do there, right? I can kind of get rid of that h by taking out a sign. So yeah, so I mean that with more practice that comes, you can see that easier, but that's the big thing, I guess. If you have like a trig problem with signs and your limit is to 0, that could be like one thing you really want to keep an eye out for. So is it okay up to this point? Like, does that make sense of like the why you're factoring that out?
yeah, that was one part I was confused on, and the second part was why the left side, like why all of that equals to 0. That was my
Yeah.
second question.
Sure. So what is this limit? Like now that we've done this simplifying, like, can we actually compute the limit now?
Yes, I think so, yeah.
Okay, so what happens when you plug in h equals 0?
You get negative sine of 0, which I don't know the value of on the top of my head.
Okay, let's if you ever forget, just draw the circle. So what's this point here?
That'll be cosine is x and sine is y.
Yeah, sine is y. So the cosine of 0 is 1, and the sine of 0.
So that'll be 0, but negative 0 is the same thing as 0, right?
Right. So I have 0 over 1 plus 1. So that whole term is 0, right?
Okay, yeah, that makes sense. So that cosine on the left doesn't matter because it's being multiplied by 0.
Exactly, yeah. It's just being multiplied by 0. Yep, so that's why I'm left over with sine.
Okay, that makes a lot more sense.
Oh, good.
Thank you.
Yeah,
I feel like I had another question, but I'm not too sure.
okay.
Um,
Is there any like realm, like maybe the stuff that we just did last time with like products and quotients and all that? I'm not sure when it came in, but we did a bunch of products and quotients rules.
Yeah, I mean, just. Sorry, I cut off there. Just generally, like a lot of the ways to just get started is by using a lot of the trig rules that we learned, right? Like if we're finding the derivative of sine of x times cosine of x, like we just start off by using some of the trig rules, like sine of x times cosine of x becomes cosine of x times cosine of x plus negative sine of x times sine of x, right? Yeah, so like, yeah, those things. So
Yeah.
that's like a good place to just get started on memorizing those, right?
Oh yeah. So these definitely these should be memorized. Derivative of sine and cosine. Those should be
Gotcha.
like top priority. The other ones, um, I think it's still good to memorize, but you can kind of derive them through quotient rule. So like if you forget, like you could just use the quotient rule to kind of like just double check.
Mm-hmm.
But you could see there's a kind of a pattern, right? Something that helps memorizing.
Yeah, there's a general pattern, but
Like the
yeah.
secants kind of look the same, they're a product of things. The tangents look the same. The derivatives of the cos are negative. Things like that. I mean, but again, like this one is the key thing to memorize because all the other ones can like you can figure out from there. But I mean, we could just do more trig ones if you want.
Um, yeah, we could do like I'm trying to figure out where I'm most confused. Um,
If you want, we could also do. I could introduce a new rule, and then we can kind of see how that applies with trig functions. Um,
I mean, sure, why not?
yeah, sure. And we will see this Monday, so maybe we could just. I'll kind of go through the proof Monday. I won't do that now, but it's very useful with a lot of trig functions. So if you have like if you have a, I'll tell you the formula, so I won't prove it now. But if you have a composition of two functions and you want to find the derivative of it, what you do is you take the derivative of the function that you're plugging into. So this is the function that you're plugging into. And whatever the derivative of that is, you plug in g, and then you multiply this whole thing by the derivative of g itself. So, so it's important to kind of understand like how composition works. So maybe I'll just do like an example, like sine of x squared. So this is a composition of two functions, right? We have sine and we have x squared, right? Those things are, it's not multiplication, right? It's not quotient, it's not any of those, but it's literally a composition. So if I let f of x equals sine and g of x equals x squared, notice that if you take f of g, right, that means you plug in x squared into x, where in f, you get sine of x squared. Does that make sense, like how that's a composition?
Yeah, I mean, so like if we were to like break that down, like f prime would be
Yeah,
cosine
right, cosine.
and then multiplied by x squared and then multiplied by 2x.
So yeah, so g prime is 2x. Yeah,
2x,
so
yeah.
what this says is that So you take f prime, which is cosine. And then
Oh,
you
I see.
plug
What?
in g.
Oh, my question just my question is leading into you actually doing the proof, right?
Oh, why is this true?
Yeah, because you're starting to. Yeah.
Yeah, so I'll prove this on Monday, but I don't want to kind of bog you
Yeah, yeah,
down
yeah,
on proof
yeah,
right
yeah,
now, but just kind of take this for granted right now.
yeah.
Yeah, so this is f prime, right? F prime, and this is g. You're plugging in g, and you're multiplying this by g prime.
Gotcha.
So yeah, I mean, it's we can just kind of do a lot of do with trig, kind of like can kind of make a lot of interesting things with trig. But maybe we can do another one if you want. Let's do sine of cosine. So when you have f of g of x is equal to f prime of g times g prime, what would your f prime, f be? So like, what is the thing that the bigger function that you're plugging into?
That would be sine.
Yeah, that's sine. And then what is the function that you plug in?
Cosine.
Yeah, cosine.
So let's just take the derivative of each. F prime is cosine, and g prime is negative sine. Okay, so when I plug this into this formula, f prime of g times g prime. So f prime is cosine, but instead of, so maybe let's even just make one extra line here. So then what is f prime of g of x? It's cosine of cosine, yeah. So it's cosine into x. All right, so we have, so then our formula for the derivative is f prime of g of x times g prime of x. So yeah, it's cosine of cosine times negative sine. So negative sine times cosine of cosine.
I mean, multiplying cosine and cosine, isn't that just cosine squared?
Oh,
X?
this is not multiplication, it's cosine of. So like,
Oh, right, because cosine x is okay, I got you.
yeah, so
If
like,
it was cosine x times cosine x, then that would be
yeah,
cosine squared x. Okay.
this is like saying like you plug,
Yeah, so you're basically finding the cosine of the cosine.
yeah, and then
Okay,
you're
gotcha.
putting that value into cosine. Yes, that's a it's a good one to do. When we do not even like sine squared. So you could do this with product rule, but I think it's easier to do this with chain rule. So this one's harder to see what the composition is, but can you think of this as a composition? And I'll give you a hint. The G, the thing that you plug in is sine. So, like, what do you think the F would be?
Oh, it's because I mean basically what I said, because sine squared x is sine squared x times sine squared x. So f of x would be just sorry. F of x would just be sine of x as well, right?
So in
X
the
squared.
product rule, you could do that, and that's fine. So, but like you could also think of this as a chain rule, where like how do you treat? Can you represent this as a composition? Is the question. I think I heard I heard it.
Yeah, fx is x squared.
Yeah, x squared. Right, does that make sense? Like if you plug in sine into x squared, you get sine squared, right? Like f of g is sine of x squared. You're absolutely right. You
Oh,
could,
okay, that makes sense. Yeah.
could do product rule where both f and g would be sine, and you'll get the same thing. Maybe when we do it, I mean, you may see how chain rule could be a little bit easier, but let's go through it. So what's f prime?
2x
2x, and then g prime,
cosine x.
cosine x. And then let's do f prime of g,
2 cosine x.
2 cosine, 2 sine, right?
Yeah, 2 sine.
Yeah, so I'm looking at g. So 2 sine. Okay, so in our chain rule formula, it's 2 sine. and
Cosine.
Okay, yeah. Do we know what that is? Is there another form you can write 2 sine cosine?
2 sine of 2x, or 2 sine of 2 cosine of 2x.
It just sine of 2x. That's the double angle formula. Yeah, you're close. Yeah, so I personally think it's a little bit, I think once you get kind of used to the chain rule, I think this is an easier approach to doing derivative of sine squared. As just sine of 2x, using the chain rule like this. Right now you may not agree because it's just threw this formula at you right now, but yeah, this is an alternate way of doing the derivative of sine squared. Actually, one that might be really helpful is like tangent squared. So much like the first one, our f would be x squared and our g would be tangent. So f prime is 2x and our g prime is secant tangent. So what is f prime of g? It's 2 times tangent. So our derivative of tangent squared is equal to 2 tangent times secant times tangent. And again, oops, I did something wrong. What did I do wrong? Something's not right. One of these derivatives is not right. That is not the derivative of tangent. Oops. What is the derivative of tangent? Is secant squared. My bad. So that's it. Does that example make sense?
A little bit.
Yeah, so again, it's using this formula. Oh, I'm sorry, f 2 tangent is f prime of g. Let's see, what's another good one? That's just something a little easier. Let's do cosine of x of 2x. So this example is kind of really good to see why the chain rule is useful. You could do this two ways, right? You could write this using the double angle formula. And then like do the product rule on each of these things. Or if you use the chain rule, you can notice that if you let f equal cosine and g equal 2x, then f prime is negative sine, g prime is 2, and then f prime of g is equal to negative sine of 2x. And f prime of g times g prime, which is our derivative, is negative 2 sine of 2x. Now doing this would take a lot longer, right? Doing the product rule and everything. It can be done, but it would just take a lot longer. Let's see. Is that better with like some examples with trig functions?
Kind of.
Okay.
I think Monday will help better understand.
Oh
No.
yeah, definitely, yeah. So I didn't mean to. Maybe throwing out chain rules too complicated. We could just do more like maybe let's do just do some quotient rules or something. Let's do sine plus cosine over x plus root x. This will be a hefty problem. So we can use the quotient rule here, right? So let's take the derivative of the numerator. Times the denominator minus the derivative of the denominator times the numerator and then divided by the denominator squared. Okay, so this is the quotient rule, right? So how do we do the first one? Derivative of sine is cosine plus the derivative of cosine is negative sine. Okay, then what's the derivative of x plus root x? So what's the derivative of x?
1.
Derivative of x is 0, right?
Is 1.
Ouch, 1, okay.
Think of the power rule. Right, x has power 1. So it's 1 times x to the 1 minus 1. And x to the 0 is 1. Other way to think about it, just intuitively, is derivative just means like slope, right? Where slope of curves are a bit more complicated, but x is just a line, so that's kind of easier to talk about. And mx plus b, it's just 1. Okay, and then root x, we can use the power rule. So we have 1/2, then times x to negative 1/2, which is radical x in the denominator. All right, and that's pretty much it. I'm not sure if there's anything. We could, I don't know. Yeah, we can just leave it like that. Yeah, maybe even, yeah, we can leave it like that. Trying to think of some other good. You think it's mostly trig that's the harder parts?
I think so. I think trig is the hard part. It requires a lot of practice and getting used to.
Oh yeah, I mean, again, I think if you just memorize these things, then it suddenly becomes not that hard.
Yeah,
Sure.
it's also with like at the start of the semester when we started talking about the simple stuff. And like unit circles and
Yeah,
X and Y values, those things. Like I like the unit circle, like I memorized it, but like kind of. So it like takes me like an extra minute to process like which value is which, and then by that point, like the function that we're working with is already at a farther point and I just get lost.
yeah, I think uh, when you have to plug things in, then you have to think a bit more. But I would definitely say like the four like endpoints of the circle are probably the most important ones to know. And then like the other ones, like I think these four ones are the ones you should kind of like know by heart. And these ones and those four ones are the easiest ones to kind of derive if you forget, right? Because these points are the easiest ones, right? It's 1, 0, 0, 1, -1, 0, and 0, -1, right? These kind of points in between are a bit harder to know, right? Kind of really have to kind of memorize those, and deriving them would maybe take a bit too long. But definitely those 4 points are, I would say, the most important. And again, that's only when you have to plug in stuff, right? Like if you're just tasked to find the derivative, you don't have to plug anything in, right? Unless it's the derivative at a point or something. But I guess you have to come to that when it happens. But I generally for my tests, I like to stick with the kind of these 4 points out here, and maybe the pi over 4 points, because those are the nice ones. Other ones, they're also nice, but I don't think they're not as nice. I would say like those are the most important ones. Maybe we could do tangent lines at a point. That would help with practice plugging in the sine and cosine. Let's do that. Let's find the slope of the tangent line of sine of x plus cosine of x. Say at, let's do it at pi, and let's also maybe do it at pi over 4. Oh, it's not. This is and. Okay, so let's do it at pi first. So we know that the equation of the tangent line is, or of any line, is y minus y1 is equal to mx minus x1. So if my x1 is pi, how do you find y1? Like, how do you find the other point? The y one is just you plug in, right, pi into f.
Yeah,
So y minus like f of pi. And what's m? What is the slope?
no idea.
That's where the calculus comes in, right? So I didn't mean slope, but equation. The slope of the tangent line is precisely the derivative, right? That's how we define.
Right, okay.
That's how we define the derivative. Yeah, so we just need to find those two values, right? F pi and f prime of pi. So f of pi is easier to look at. For practice, why don't you tell me what it is? And again, pi is over here. And all you really can do is find the point. So what's the point there?
-1, 0.
Yeah. So then what does that tell you, sine of pi?
It's 0,
Yep. And then cosine?
-1.
Right. So we have y minus -1 is equal to f prime x minus pi. That's y plus 1. Okay, so now let's find, now our goal is to, what is f prime? Okay, so what is f prime of x?
1. No, that was the x squared.
Sorry, not f prime of x, but f prime where f of x is equal to sine and cosine.
Oh,
Yes, the derivative of sine is cosine,
yeah.
and
I was
derivative of
thinking if it was
cosine.
negative or not, but I guess it's the derivative of cosine is negative sine x.
Yeah. So one thing, good thing, kind of like a mnemonic device, like if you could call it that, all the co-functions, the derivatives are all negative. So cosine is negative, cotangent is negative, and cosecant are all negative. They're
The
derivatives.
derivative of those three. Okay.
Yeah. And the other ones are positive. Okay, so now let's plug in pi. So cosine of pi,
-1
and sine of pi.
-0.
Yeah.
So just -1.
Right. So our tangent line is y plus 1 is equal to -1 x minus pi. Or you can write it in mx plus b form if you want, -x plus pi minus 1.
That makes sense.
Okay, cool. Oh yeah, maybe we could do a pi over 4 as well. So we can like just go to our derivative or our equation of the tangent line. So it'd be y minus f of pi over 4 is equal to f prime of pi over 4 x minus pi over 4. So do you remember what sine and cosine of pi over 4 is?
I over 4 is like the halfway point between
Good, yeah.
yeah, that place. The x and y.
It's one thing to
I
remember
think
that they're the same.
Sorry, I cut off again. What did you ask?
Oh, that the sine and cosine of pi over 4 are the same value.
I think it was square root of 3/2, if I'm not mistaken.
That's that like
No. Yeah, that's another one. Dang.
it's okay.
1/2.
It's root 2/2.
√2/2. Okay.
That's okay. One way, if you forget, sometimes I like to do this. So unit circle is hypotenuse 1, right? That's what it means to be unit. And pi over 4 is just 45 degrees, right? So you actually get an isosceles triangle, right? If one of your angles is 45.
Yeah.
So these are the same, which is true, because if sine and cosine are the same. So then you can just do Pythagorean theorem to figure it out. So this is the rationalized form and this is not rationalized, but either one are fine.
Right.
One thing to remember, this is kind of more just seeing a pattern. The numbers that appear most frequently are all of the form, they're all divided by 2, right? And they're
Yeah.
ascending 1, radical 2, radical 3. So really, it's just radical 1/2, radical 2/2, radical 3/2. It's a good way to kind of memorize.
Yeah, that makes it a lot easier.
Yeah. So the halfway point, 45, they're the same value. 1/2, this is the smallest. So if you think about it in the unit circle, it's how I like to think about it sometimes, that if you're at the smallest angle, or sorry, so the angle that's closer to the x-axis, which is bigger, the x or y value? Like if your point is closer to the x-axis. Oh, okay, get the head out. Okay, maybe I can just say like, so the smaller and larger values can kind of tell you, since I'm closer to the x-axis, I should pick the smallest of the 3 values. And since I'm pretty far away from the origin, my x value is bigger. And if I'm up here, I'm high up on the plane, so radical 3/2, and I'm closer to the y-axis, that makes me 1/2. But either way, so all right, so let's see, plugging in pi over 4 into this, we get, so radical 2/2 plus radical 2/2 is radical 2. And then if you plug in that into f prime, well, if they're both radical 2/2, then cosine minus sine of that is 0. So my line is y equals radical 2. So it's actually a horizontal line at that point. All right. Yeah, I just realized it's kind of late too. Maybe does anybody have like a specific question they would want to ask? But if not, I can head out. It's already almost 2 hours, so. So I'll leave it to you. If you have like a specific question, please let me know. If you just want to see more problems, I can do that too. I'll just leave that to you. So maybe like type in the chat, like, what would you want to see? You want to see more problems, or should we call it a day? All right, let's see an answer. So I think I'm gonna call it a day, but I can post these notes if you want. Just some of you may have come in a little bit later. I can post these notes and I'll record this. So okay, I'm gonna head out. I'll stop recording.